Endo and exothermic processes involve a change in heat, but very often we think of endo and exothermic as reactions. So, not just things that are increasing or decreasing in temperature or changing in phase, we're thinking about chemical changes. So, with a reaction, we are breaking some bonds in our reactants and making some bonds in our products. And that process of making and breaking bonds exchanges energy. It has to do with potential energy. It has to do with the strength of that attraction. And one of the most important things that we can do to understand thermodynamics and connect it to atomic structure, to bonding, to intermolecular forces is to think about the energy exchange when breaking and making bonds or attractions. So first and foremost, when things are bonded together, they are already attracted. They are stuck together like two magnets, and breaking that bond requires energy. You're going to see the same thing, these same colors, a couple different places in bold, all caps letters, because it's super important for us to not just see this and hear this, but remember this. Breaking bonds requires energy. And then when bonds are made, when we rip our magnets apart, but now we rearrange and allow those to come back together, they click together or they give off energy. Making bonds releases energy. So that's very important to have that straight in our mind, that the breaking is an endothermic process and the making is an exothermic. And in most chemical changes, we're doing both. Even if it's not super obvious that we're doing both by the reaction, the way that it's written, there might be some interparticle forces, maybe some metallic bonds or some bonds that we're not even thinking of being broken that are being broken initially. So an endothermic reaction is still defined as one that requires energy. That would mean that the energy that's flowing in is greater than the energy that's flowing out. And specifically, the energy of the breaking the reactant bonds is a lot. The energy released when the product bonds are made would be less. So we see that, and we can see that right here. We have to put in a lot of energy to go up that hill. And we know that that is the activation energy. But we come back down the hill, meaning there is a release of energy, but that downhill is not as big as the uphill. Overall, in an endothermic process, heat is taken in or absorbed. So we have that uphill. So we have both in there, but the in is greater than the out for endothermic. And it's really easy to say those backwards, as you can hear. Exothermic is exactly the opposite. We still put energy in, and we put energy in first. We can think of this in terms of kinetics, in terms of thermodynamics, in terms of bond energy. It's still an activation energy. That uphill, we have to overcome that before the process can start. So even something like building a campfire that's going to give off lots of heat in the long run, we still have to give it that activation energy. Or you might still have to provide a spark to start that. Even to burn a candle, we still need to provide that spark. So the energy required, though, is less than the energy released because the total strength or the total energy of the reactant bonds, which are the broken bonds, is less than the total energy released when the product bonds are made. We've got a small uphill and a large downhill. Overall, we still may need to put in a little bit of energy to start, but then these reactions very often continue on their own. Overall, from start to beginning, though, our delta H, or our heat, is negative. So here, and we'll see this later, positive and negative in terms of our changes in energy or changes in heat. So the extra energy in both cases is either flowing in or flowing out. And in that case, we're just talking about the difference between the two. When we're thinking about reactions, sometimes kind of mixed in there is the process of something dissolving. So chemical reactions make and break bonds. When things dissolve, we also make and break attractions. Sometimes those attractions are actually bonds. We might break an ionic bond. We might break a covalent bond within an acid or an ionic compound, or we might just break an intermolecular force between to particles in a polar or a nonpolar molecule. But in all cases, we are breaking an attraction and we are making new attractions if the things are mixing. The attraction that we are making is between the solvent or the liquid, very often the water, and the thing that got dissolved. Sometimes these are endothermic because it takes a lot of energy to break that apart. But very often these are exothermic because it's a very favorable, a very likely, or an energy releasing process overall. For both, we follow the same idea that we are breaking things apart, we are putting things together, and we have an in and an out in terms of the flow, and we can see which one is greater and compare those as well. We'll notice that a lot of things, when they dissolve, they don't get very hot or very cold because we have a very similar energy in both directions.